Hello, everybody. This is John Ross, and I'm here to continue with our exploration of place value, and specifically our base 10 system. Our learning objective is as follows. I can understand that in a multi-digit whole number, a digit represents 10 times what the same digit represents in the place to its right. For our activator, I want you to take about 20 seconds to silently analyze the blocks that are found on the screen. And I want you to think about how you've used them in the past, what they might be used to represent. And at this time, we will go ahead and start the clock. You have 20 seconds to silently analyze those blocks now. All right, 20 seconds has come to a close. If you have a friend, sibling, mom, dad, aunt, uncle with you, and you want to pause the video and share your own observations, please feel free to do so at this time. All right, whether you share those observations or not, I'm going to go ahead and share my own now. And it'll be interesting to see if you had the same observations that I had. I first want to start out by noting just what each of these blocks is referred to as, what their names are. We have a unit. This is a unit. Here we have a rod. Here we have a flat. And here we have a cube. I also want to note that a unit can be used to represent the whole number 1. A rod can be used to represent the whole number 10. A flat can be used to represent the whole number 100. And a cube can be used to represent the whole number 1000. But I also want to note why they can be used to represent those various whole numbers. First, well, here we have just a single teeny tiny block, and that is why that teeny tiny single block can be used to represent the whole number 1. While a rod that you have likely used many times is long and a single piece as far as what is comprised of within our hands, if we look closely, we can note that basically we have 10 of those smaller units that have been placed together to form that rod. So that's why a rod can be used to represent the whole number 10. Here we have a flat that we said can be used to represent the whole number 100. And we know that a flat can be built out of 10 rods. And if a rod has a value of 10, which it does, and we have 10 of those rods, that's kind of like saying 10 times 10 equals 100. Similarly, if we have this cube, which we say equals 1000, I know that a cube can be built out of 10 flats. And if a single flat has a value of 100 and I have 10 of those, that's kind of like saying 100 times 10 equals 1000. And so I also want to note that each of these blocks has a value that is 10 times greater than the value of the block to its right. So our rod has a value of 10. And it has a value that is 10 times greater than the value of that unit, which is 1. And we know that to be true because 1 times 10 equals 10. This flat has a value that is 10 times greater than the value of the rod. And we know that to be true because it takes 10 rods, 10 times 10, because that rod has a value of 10. If I've got 10 of them, 10 times 10 equals 100. So that flat has a value that is 10 times greater than the value of the rod. And my cube has a value that is 10 times greater than my flat because it takes 10 of those flats to make a cube. For our first I do, we have 222 right here. And we're going to fill in our place value chart here as best we can. And so first, this 2 is in the hundreds place. This 2 is in the tens place. This 2 is in the ones place. So now that we have our digits in the appropriate place, we can then move on to representing that number, but specifically each digit with base 10 blocks. And so if I've got 2 hundredths, I need to use 2 flats. So I could place 2 flats here, or I could put 2 drawings of a flat here. 2 tens can be represented using 2 10 rods, or drawing 2 10 rods. And then I've got 2 ones, which could be represented using 2 units. Finally, I want to note the value of the digits. So here I have 2 hundredths or 2 flats. So the value of 2 flats, or the value of 2 hundredths, is 200. Here I have 2 tens or 2 rods, and if I have 2 tens or 2 rods, the value of those are 20. And then I have 2 ones or 2 units, and the value of those 2 units is 2. Now, just for fun, if I want to, I could put a plus sign between my 200 and my 20 right here, and my 20 and my 2 right here. And what I have just done is represented this number in expanded form. So we have 222 in standard form right here, in model form right here, but then we also have it in expanded form. I want to take things a little bit further, and I want to note that if I were to take the value of the 2 in this place right here in the ones place, and I were to multiply that value by 10, 2 times 10, the resulting product would be 20. And so that tells me that this 2 is 10 times greater in value than this 2. Similarly, if I wanted to take the value of the 2 in the tens place, which is 20, and multiply it by 10, the resulting product would be 200. And so that tells me that this 2 in the hundreds place has a value that is 10 times greater than the 2 in the tens place. So we're going to do this exercise one more time, but this time with 333. So I've got 3 hundredths, I have 3 tens, and I have 3 ones. Here I have, I'm being asked to represent each digit as the appropriate base 10 blocks. And so 3 hundredths would be represented with 3 flats. 3 tens would be represented with 3 rods. 3 ones would be represented with 3 units. And finally, I want to note the value of each digit. 3 hundredths, 3 flats. The value of 3 hundredths is 300. The value of 3 tens is 30. And the value of 3 ones is 3. And just for fun, I can place a plus sign between 300 and 30, 30 and 3, and now I have represented my number in expanded form, model form, and here it is as it was found initially in standard form. But I want to take things further so that we make sure that what we're doing is aligned to our learning objective. And I want to note that if I were to take the value of the 3 in the ones place, which is 3, and multiply it by 10, the resulting product would be 30, which is the same value as the 3 in the tens place. And so again, that tells me that the 3 in the tens place is 10 times greater than the 3 in the ones place. As we've done before, If I wanted to take the value of the 3 in the tens place, which is 30, and multiply it by 10, the resulting product would be 300. And so that tells me that the 3 in the hundreds place is 10 times greater than the 3 in the tens place. And now we're going to complete these few multiplication problems, and while doing so, I want you to look for any sort of patterns that you might see. And so our first one is 7 times 10, which is 70. 70 times 10, which is 700. 700 times 10 is 7,000. 7,000 times 10 is 70,000. 70,000 times 10 is 700,000. And 700,000 times 10 is 7 million. And so one thing that I notice, an observation that I make, is that when I look at my factor sets, 7 and 10, for example, if I have 1 0 over here, I should have 1 0 for my product, or within my product. Here I have 2 zeros, so within my product, 2 zeros. Here I have 3 zeros, so I have 3 zeros here. 4 zeros within my factors, 4 zeros within my product. 5 zeros within my factors, 5 zeros within my product. Here I have 6 zeros within my factors, and I have 6 zeros within my product. So that is one interesting observation that I can note. And another little interesting tidbit is if I look at my first factor, and since I'm multiplying all of these first factors by 10, the digit of value, and we have 7 as that digit of value, its location differs from equation to equation, but because I'm always multiplying that first factor by 10, I'm moving that 7 over one place value to the left each time. So 7 becomes 70, 70 becomes 700, 700 becomes 7,000, 7,000 becomes 70,000, 70,000 becomes 700,000, and 700,000 becomes 7 million. And so what we're really trying to illustrate here is that a number that's 10 times greater than 7 is 70. A number that is 10 times greater than 70 is 700, so on and so forth. So here we're going to kind of analyze this number, which is 4,962. Notice that the 6 is underlined. We have 3 numbers that are built out of the same digits, but those digits have been scrambled. Our question is, which number has a 6 that has a value that is 10 times greater than the 6 in 4,962? This 6 is in the tens place. I want to know which of these numbers has a 6 that is 10 times greater than the 6 in 4,962. So if need be, I can say, well, that 6 right there, that has a value of 60. So if I multiply 60 by 10, the resulting product is 600. So which of these numbers here has a 6 in the hundreds place? Ah, yes, it is the 2,694. For our next I do, we have 382,794. And again, we've got 3 numbers which have the same digits within them, but they've been scrambled. And our question is, which number has an 8 that has a value that is 10 times greater than the 8 in 382,794? At this point, hopefully you're catching on that basically this 8 has a value of 80,000. If I were to multiply that 80,000 by 10, I would get 800,000. So which of these numbers has an 8 in the hundred thousands place? The answer is 874,923. And our last I do, we have 58,419. We have three numbers which have had their digits scrambled. They are comprised or built out of the same digits as are found in 58,419. They've just been scrambled. And our question is, which number has a 4 that has a value that is 10 times greater than the 4 in 58,419? So I hope that you're able to now see that basically I need to say, well, I got a 4 here, I got a 4 here, I got a 4 here. Which of those digits is basically one place to the left, and that is this one, this number here, 94,185. And I can prove that to be true by saying 400 times 10 equals 4,000. And so that's how I know that 94,185 has a 4 that is 10 times greater than the 4 in 58,419. So at this time, I'm going to invite you to complete your Schoology assignment for some independent practice. Thank you for joining me.